In this problem, we have a block on a frictionless incline, which is free to slide. So it slides down from here and then gets into contact with the spring and compresses the spring. The question is, what is this distance d along the incline if the compression of the spring at the moment when it stops, when the block stops, is known? Let's say delta x. So in this problem we will have to ignore the size of the block itself. So let's say that this is the center of mass of the block, which is the initial position, and then the final, after the block has compressed the spring and stopped, this would be the position of the center of mass. So let's say that it is at a distance delta x from the original position of the spring. So the question is, what is then d equal to? Well, let's first define our system. Let's say that my system is the block, the spring, the incline, and the earth. If I define my system like this, saying that it's the block, the spring, the incline, and the earth, I can see that my system becomes isolated because there are no external forces acting on the system. Well, if the system is isolated, it means that the total mechanical energy initial and total mechanical energy final have to be conserved. There is no heat, so instead of talking about total energy, I just talked about total mechanical energy here. So total mechanical energy initial would be equal to potential energy initial plus kinetic energy initial. Total mechanical energy final is equal to potential energy final plus kinetic energy final. Now, first of all, we know that the block starts from rest, so kinetic energy initial is 0. And at this position, the block is again at rest. So kinetic energy final is 0. Now, obviously, after it comes to rest, the spring will decompress, but we don't worry about that because we only are worried about the point when it comes to rest. So this is our final point. So both kinetic energies are 0. So what about the potential energies? Now, when we talk about potential energy, we have to keep in mind that our system includes the spring as well. So the potential energy will consist of two potential energies basically: potential gravitational energy and potential elastic energy of the spring. So let's start with the potential energy final. Now remember that for a gravitational potential energy we need to define the 0 level. So let's say that this level corresponds to 0 level of potential energy. So the potential gravitational energy in the final state is equal to 0. What about elastic potential energy in the final state? In the final state, the spring is compressed by delta x, and as we know, the potential energy of the spring is equal to k delta x squared over 2. So this is the total potential energy final. Now what about potential energy initial? In the potential energy initial, the spring is not compressed and is not stretched, therefore has no potential energy, but the mass is up here. So it is at a height h. So we can say that this is equal to mg h. So now we need to find this h. Well, if you look at this triangle here, the hypotenuse here is equal to delta x plus d. And the angle that the hypotenuse makes with the ground level is theta. So h, therefore, is equal to the hypotenuse, which is d plus delta x times sine of theta. So we can use that and plug it into this equation. So we have mg d plus delta x sine theta equals k delta x squared over 2. So this can now be used to calculate for d. So let's erase this picture. So from that equation, d is then equal to k delta x squared over 2mg sine theta minus delta x. Now we are given the spring constant, the compression delta x, the mass, the angle, and we know the free fall acceleration, so we just can plug the numbers in, and we calculate the d to be equal to 2.289 meters. So this is the original distance d.